So today I'm going to talk a little bit about FSMs, and I'm going to at least walk through the process and work through some of the steps for working with FSMs, and in particular trying to get from an FSM to a circuit. Now, before I get into any tables or any particular FSMs, I want to make sure it's very clear what exactly we're trying to do here. So let's say you have just some FSM. So I don't know, I'm going to just draw something arbitrary. Doesn't really matter. And let's say we start with something. I won't try the whole thing, but yeah, let's just say we have this. So let's say we have an FSM, and we have a binary input and a binary output. This binary input can be multiple bits, maybe. The output can be multiple bits. It doesn't really matter. It doesn't really matter how many states there are either. So the goal, or our goal, is to take an FSM diagram like this, which is just some drawing. It just represents something, and convert it into a circuit with, let's say, input X, output Z, and then we also are going to need a clock just to be able to actually process inputs. Basically say, use the clock to say, okay, now I'm giving it an input, now I'm giving it an input, now I'm giving it an input. And the clock is sort of just going to be able to tell us when we want to move to a next state. Because obviously you could just give inputs as quickly as the circuit can take them, but that's really hard to work with. So we use the clock signal here, or we use a clock signal to be able to control precisely when the FSM is going to move from one state to the next. So we can say, let's say if the clock is 0, we'll just stay where we are, and when the clock is 1, it'll update based off of whatever X is at that moment. And then we can turn the clock back off, turn it back on, and it'll process the next input, and so on. So how do we do that? How do we go from this drawing of a state machine into a literal circuit that does the exact same thing, that given certain sets of inputs and certain sequences of inputs will produce the same outputs that this FSM does? So it turns out that you can sort of take one of these FSMs and you can split it apart into basically two parts. You can split it apart into the logic and then the state, which might seem like a pretty basic thing to say, but the whole idea here is that we can implement all the logic using combinational methods. Like, it's just a combinational component, same way that we've been doing since the beginning of class, until we started FSMs, right? You just have some inputs and it always produces the same output. And we can do that by essentially, instead of just creating a function that takes inputs and produces outputs, we are going to create a function that takes inputs and the current state and produces outputs, whatever Z is, plus whatever the next state needs to be. And all of that logic can go into here. Then all we have to do is hook this logic up to the state, which we will store maybe using D latches, maybe using Sr latches. And at that point, we're done. We've created the FSM. And so by splitting apart the problem, we can handle all of the logical components in a method that we already know how to do. And then the state is just something that a little bit of nuance that we have to do and handle at the end. Okay, so let me quickly put together an arbitrary FSM that we will use for this. Something I want to note is that an FSM is not necessarily a sequence detector. Sequence detectors are FSMs, but FSMs can represent a whole lot of different things. So in this class, we take a look at sequence detectors because they're very good examples of binary FSMs with binary inputs and binary outputs. But really, there's not any reason that the inputs need to be binary. They could be pretty much anything. But we'll just stick to inputs and outputs being binary for simplicity. And I'm just going to use one input, one output. Let's see, let's go here. And then let's say here. That's that one, that one, that one. So just need this one here. Let's see. And then, let's see, I'll just do this here. Okay. So, I mean, like, notice here that I have two arrows coming from this one, whether it's 1 or 0. That's perfectly valid as an FSM. As a state detector, like as a sequence detection machine, that wouldn't really work. That wouldn't be able to detect sequences, but in all other cases, it's fine. Although, actually, it might be possible for some sequence detectors to look like that, but... Okay, so... I'd also just call the states random. Well, I'll call maybe this one A, B, C, D, right? And yeah, this is like completely random. I just drew something up, and that's what we'll use. And just to sort of the goal here now that we actually have something concrete, well, we need to figure out first how many states we have, or we have 4 states, right? 4 states. So the problem is, how in a circuit can I just store, hey, I'm in state A? Like that, circuits and memory components can store zeros and ones. They can't store, hey, you're in state A. However, we can give a binary representation of each of these states. So maybe for A, we can say that it's 0, 0. For B, it's 0, 1. For C, it's 1, 0. And for D, it's 1, 1, right? This can pretty much be arbitrary. It might be given to you in a problem, or you might have to figure it out, but really, it doesn't matter. Whatever you choose, you can ultimately make a circuit for. So our state is going to be 2 binary variables. And so that means that we ultimately want to create a picture like this. We want to create our main logic, which is just going to be normal combinational logic. We'll essentially want to just come up with a table for this and just solve for each of the equations using some known method, or implement them using muxes or whatever. So then we'll have our next state. I'm going to call them N1 and N2. And then we'll say that the input here is our current state, Y1. And I'll actually do Y0. So Y1 and Y0 is going to be our current state. And then we need to somehow output something such that we can pass it into a memory component, and that memory component will update properly. So the output here isn't really the next state. It's going to be how you update to the next state. So if we're, let's say, using D latches, then we might have D1 and D0 here. And so now we could have our D latches here. We'll say that Q's here, D is there, and Q's here. Just like flip it around just so that it's easier. And we'll have another one of these here. And then we can go ahead and wire up, let's say, D0. And take Q and wire it up here. So that way, this right here is going to hold the state of Y0. Right, and so it outputs the state, and we'll pass that into our logic because the logic needs the current state. And then whatever the state at some point is going to compute, oh, hey, the next state, in order to properly update to the next state, send this input here to the D latch, and the D latch will just update when you send it a clock signal. And I'll represent the clock just by this little arrow here. And I'm not going to connect it up, but it will be connected up just somehow. We don't really worry about that. It's just timing issues. But there is that clock hooked up there. So then we can take D1, do this, and then take Q and hook it up to Y1 like this. I do ask that you make sure you're muted if you're not asking a question. So this is one possible way that we'll implement the FSM, right? We don't necessarily know what this is, but we can essentially create a table and then just figure out what it is. But our goal is either to create this, or alternatively, we can use SR latches instead. So we have the same exact picture, but using SR latches, although the logic is going to be slightly different, right? Because we have S and R instead of just D. So here we'll have X, Y, X, Y1, Y0, input, current state, output, and then here we'll have S1, R1, S0, R0, and these will represent what we pass into an SR latch so that it updates its state properly. And here we'll use a clocked SR latch just because we want the clock to be able to synchronize everything. And so we'll have X and Z here. Those are just our inputs. I put a Y there. Z. X and Z, they're just our input and output. Those just will go to the input or output of the FSM component, right? That's just, this fits all inside of the FSM component. Then let's say, I'll just draw one of them because there's a lot of wires, but we'll have our SR latch here, Q. This Q here will be hooked up to, let's say, Y1, and then we'll take S1 and R1 and hook them up here. So now, again, we'll have a clock. So now when we update the clock, it'll take the S1 and R1 out of this logic and then just pass those straight into the SR latch, and the SR latch will just magically update itself. And I say magically, but the whole point is we're going to figure out what needs to go in here in order for that to work. But this is the goal. And also we would have another latch here, and we would hook that up. But the point is that we're either going to make this or we're going to make this. That's the goal. Yeah. Oh, yeah. Sometimes Discord can get it roboty. But yeah. So the goal is this or this. And keep that in mind. It's always the goal. The goal is to go from an FSM diagram to making this circuit or making this circuit. And so, like, I will constantly get the question, once we fill out the table and we solve the equations, what do? It's this or this, always. Right? That's the whole point. The whole point of doing the table, solving the equations, is so that you just have to fill in this stuff. Right? The rest of it is going to be connected exactly like this every single time. Well, you might have more states, you might have more inputs, more outputs, but same thing. Okay, so now we can actually go ahead and get started on working on this component here, because this is exactly, now it's a little bit more clear what we're trying to do. We're trying to figure this thing out. Okay, so the first thing is I'm going to start with just a state transition table. I'm going to ignore the state encoding here for now. That was a horrible box. But I'm going to ignore this for now and just do a state transition table in terms of the just arbitrary state variables. And then I'll just slowly start replacing things in so you can sort of see all of the different steps you might go through. So the first one is literally just to, let me see, let's copy, actually I'll move this here. Let's move this down here. Okay. So what we want to do here, we'll have our current state. I'll just represent that as C. We'll have our input X, and then we'll have our next state and output Z. And here we're going to create a table, but it's not really a truth table. This is just going to be some table that will help us to at least convert this into just a set of rules instead of looking at this weird image. So we can, at any point in time, let's say we can be in state A, you can be in state B, you can be in state, actually that's a little bit small there. Yeah, that should be a little bit better. Oh, come on. Okay, there we go. Okay, sorry. current state, which we can maybe say is A. Then we have B. I'm drawing these pretty big because I'll subdivide these just to make it a little bit clearer. And then D. Okay, so now we have our inputs. Now for each of these, I can have an input of 0 or 1. And then we have our next state and our output Z. And the whole point now is that we just want to fill out this table here. According to what the FSM diagram is telling us. Okay, so now let's just start with state A. So if we're at state A and we see an input of 0, so that's going to be this branch here. Remember, the first one here is the input, the second one is the output. So for an input of 0, we'll go to state D. So the next state is going to be state D. And then we'll output a 0. And you just want to do that. You essentially want to look at every single one of these arrows here and then just translate that into a row in this table. So we have A input 1, that's an output of 0, and we're going to go to state C. And then we have from B, we can get a 0, go to state C, output a 0. From B, we can get an input of 1, which we would go to state D and also output a 0. From state C, we can input a 0, end up in state D and output a 0. If we're in state C and we see a 1, we'll stay in state C and output a 1. And then if we're in state D, well, regardless of whether we input a 1 or a 0, we'll go to state B. But when we see a 0, we'll output a 1, and when we see a 1, we'll output a 0. And so this is our state transition table. And here again, we have these sort of variables here, but now all we need to do is we just need to look back at this state encoding here, and then just plug these values in, and now we have a truth table. So I'll go ahead and do that. So we'll move over here. So now, but I'll also replace it with state variables. So instead of C, I'll represent that as capital Y1, Y0. Then we'll have our input X. And we'll have the next state, which I'm going to use N1 and N0. I typically try to avoid using like capital and lowercase letters, especially if I'm writing it out, just because that can get confusing. But yeah, and just represents for, I just use for next state, and then Z. So now, let's see here. Go ahead and just make all of my rows. And yeah, this table doesn't necessarily need to be in any order either. I mean, I did A, B, C, D, but there's not necessarily any order that the states should be in. It does help, however, that this truth table here that I'm making now, this one, it is helpful to have it in this order, you know, in the binary counting order, so that your inputs, you have 0, 0, 1, or 0, 0, 0, 0, 0, 1, 0, 1, 0, you know, how you're normally used to seeing a truth table. This table should be in this order. So, like, let's say for A, you chose the state encoding 1, 0, 1, 1, 0, 0, 0, 1, right? You would sort of want to reorder this in this table so that it matches like that. But I'm just going to use a 0, 0 for A, 0, 1 for B, 1, 0 for C, and 1, 1 for D, because that way it'll just translate directly. Again, the state encoding can be you can choose it to be arbitrary. The problem is that how simple your equations are depends on what your state encoding is. But it's actually kind of difficult to make sure that you choose a good state encoding that results in nice simplified equation. That's a very difficult thing to do. So for the most part, we might just give you what the best state encoding is. And that is usually worked through by exhaustion, or the FSM is designed in such a way where it's sort of obvious what the state encoding should be. In this case, I have no clue what this FSM even represents. So we'll just use this and that'll be good. So I'm just going to go ahead and fill out this table, just like the inputs for this table, just like you would do anything else. And now we'll transfer over. So now state D, we'll use this state encoding. So state D is 1, 1. State C is 1, 0. Then we have another C, which is 1, 0. Then D, 1, 1. D is 1, 1. C is 1, 0. B is 0, 1. And B is 0, 1. And we can notice here that the next state is never A. Here it is, which we can see because there's no arrow going into A. So maybe you start off in state A, and then when you see a 1, you go here, and then you just stay in these 3 states forever, right? You'll never go back to A, but you needed to start out here to know whether you should start in C or D or something like that. Depending on your context, that might make sense. And then Z here is just going to be exactly the same. So now we have a truth table. So we've gone from this arbitrary picture here to saying we want to make this or this, to now we have a truth table for exactly this. And now you're pretty much done, right? You know how to go from a truth table to a circuit. So here we will, so again, remember the way that this is laid out is we have, there's one more step after this, right? We have the next state, but what we want is either how do we input into a D latch or how do we input into an SR latch so that it properly updates to the next state. And that'll be a little bit more clear. It's a little bit convoluted at the beginning, but that'll become more clear. But yeah, so we could come up with the equation for Z, but we'll go ahead and wait for that. So let's start with the D latch ones. So I'll go ahead and just add some extra columns here. Okay, so we'll have D1 and D0. So now the question you want to ask yourself for this column is what do you have to input? And you'll just do this for every single pair of inputs. So we'll just look at D1 here, which will correspond to Y1 and N1. So let's say we have a D latch, and it'll help here to draw a picture. So let's say I have a D latch here, and it's currently holding whatever Y1 is. Right, so in this case, it would be holding a 0. And we want to pass something into the D latch so that when we send a clock signal to it, it'll then be a 1. Well, it's a D latch, right? So the way that a D latch works, let me quickly draw a table for it. So you have the clock, you have your output Q. If the clock is 0, the output Q is just going to be, Q next and then Q current. So if the clock is 0, the next state is just the current state, and if the clock is 1, the next state is just going to be D. And so we know we're going to set the clock to 1 at some point. That's sort of the whole point, is we're using the clock to synchronize everything together. And so we're going to set the clock to 1, and when we set the clock to 1, that's what it's going to write. So if we want this D latch here to hold whatever N1 is, we sort of have to pass in N1 exactly as D, because otherwise it won't store that properly. So because we want it to, if a D latch is holding a 0 and we want it to hold a 1, we have to pass in a 1 because we are going to be setting the clock to 1, right? Otherwise, it's just going to be maintaining when the clock is 0. And if you've probably already noticed this, but the D1 and D0 columns are always just going to be identical to the N1 and N0 columns, and that's just because that's how a D latch works. In order for the D latch to hold this state, you have to pass it in what you want it to hold. That's just how a D latch works. So for D1 and D0 here, it's just going to be exactly the same as N1 and N0. And that's always the case. That's just because of how D latches work. And it's also one of the main reasons why D latches are nice to work with, is because it really is that simple to figure out what you need to write. For the SR latches, it gets a bit more complicated. So I'll start off with S1 and R1. So so now here for S1 and R1, both of these are going to be for these two. So now we're going to ask if we have an SR latch here that is holding the value of Y1, right? What do we have to pass into S and R such that the state will update and become N1? Okay, so now this is a bit more difficult because an SR latch is more complicated, at least to use, than a D latch, right? We can't just say, oh, pass in a 1 and say, okay, well, now it'll hold a 1, or pass in a 0 and then it'll hold a 0. We have two inputs and we have to manipulate them in a specific manner. So typically when I do this, before I start, instead of trying to work out the logic behind exactly what I should be putting here such that happens, I'll just make a small table. And I don't memorize this table. I work it out every single time. One, that helps reinforce your understanding of SR latches, and two, it's not that hard to work out. And it's much easier to remember how to work it out than it is to just memorize the table. So here, we'll just have all possible options of the current state and the next state. So this is not a truth table. This is like a lookup table. This is just meant to say, if I see this, then I want to put this. Okay, it's not a truth table. So if I have an SR latch that holds a 0, and I want it to hold a 1, well, let me actually first draw out the truth table for an SR latch. We have 0, 0, that's Q current. 0, 1, will hold a 0. 1, 0 will hold a 1. And then 1, 1 is invalid. So essentially, our options here for S and R are essentially to put 0, 0, 0, 1, or 1, 0. But we also want to, it might be possible that we don't really care what R is, or that we don't care what S is, and in which case we want to put that, because the whole point is we want to take this table then and minimize it somehow. And if you have don't cares in your equation, you can minimize it further. So let's consider this. So if the current state is a 0, so like here we can just pretend that this QC here is just equal to 0, right? And we want it to hold a 0. Well, which of these two rows in this table are 0? Well, it's these first two, right? Because we're assuming here that the current state is 0, so that means QC is 0. Well, what could we input so that the output would then be 0? Well, it's either of these two. So that means we can input 0, 0 or 0, 1. In either case, S has to be 0, but we don't care what R is because it could be 0 or 1. And regardless of what it is, we're going to end up with the right output. So we'll put a don't care here. And you essentially want to just do this for every single row here. You want to basically ask yourself, if an SR latch is holding something, what do I have to input into it to hold something else, right? If it's holding this, what do I have to input to hold this? Another way you can think of it is, it's holding a 0 and you want it to hold a 1. The state is changing, right? So you obviously don't want to maintain that. That wouldn't work there. You obviously are changing it from a 0 to a 1. So it has to be this one. It has to be 1, 0 because it's holding a 0 and you want to change it to a 1. And the only way to set it to a 1 is with this specific input. You can't maintain, and obviously resetting it back to 0 wouldn't be helpful. Then if it's holding a 1 and you want it to hold a 0, again, you can think here. Well, the current state is going to be 1, and you want to find all the rows where the output's a 0. It's going to be this one, right? That's the only one where the output is a 0. So you would put a 0, 1 here. And then, then for 1, 1, the current state would also be a 1 here. But now we want to find the rows where it's a 1. That's going to be these two. And we can see R is always 0, and S is 0 and also 1, so we don't really care what it is. If we can put anything there. If we put a 0 here, it'll work. If we put a 1 here, it'll work. It's not that we don't care about what, let's see. It's not that we don't care about S, it's that we don't care what S is, because regardless of what S is, we'll still get the right output. That's the point of the don't cares. So you can sort of fill out this table, and once you have it, now you can just easily look up. So now we can say on this first row here, so let me grab some color here to highlight. extra layer. There we go. So if the current state is a 0 and the next state is a 1, well, that corresponds to this right here. So we can just put 1, 0. Right? And once you've worked out, the whole point of working out this lookup table is just so that you have it and you can easily look it up. Otherwise, you could work. You could say, okay, if an Sr latch is holding a 0 and I want it to hold a 0, I would have to input, and I want it to hold a 1. I have to input 1, 0, right? You could do that, but it's probably just easier to do this, and you'll make less mistakes as well. So yeah, that'll be 1, 0. If it's holding a 0, you want it to hold a 1, that'll be 1, 0. If it's holding a 0 and you want it to hold a 1, also 1, 0. 0 to 1, that's also 1, 0. 1 to 1, now that's here, don't care 0. And again, just to make it clear, we're holding a 1, you want it to hold a 1, so we'll put don't care 0. And remember, we're only caring about y1 and n1. We'll have to do a second set of columns for y0 and n0. Then we again have, let's see, erase that. So then we have, it's holding a 1, we want it to hold a 1, that's the same exact situation, don't care 0. Then we have holding a 1, what we want it to hold a 0. That's this back to this column here. And that is going to be 0, 1. Or that's a different column. So yeah, that'll be 0, 1, 1, 0, also 0, 1. And that's what you have for SNR. You can sort of notice, interestingly, that every single place that D1 is a 1, you sort of have a 1 here. And then sometimes where you have a 1, you have a star. And then sometimes where you have a 0, you'll have a 1 here, or maybe a star here. That's just sort of how it works and why you can sometimes minimize SNR more. You might think that, oh, well, D-Latch is always going to end up being better, but that's not true. It's very much possible that because of these don't cares, this simplifies more. So that's why it's worth doing both before you implement, because at least in theory, the whole idea is you're doing this work so that you can implement a circuit. Well, once you've already implemented the circuit, it's kind of a waste to say, oh, well, actually, we probably should have made it this way so that it would have been cheaper or run colder or whatever it may be. So it's worth doing this work by hand so that once you actually make it, you don't have to try to change it, because it's obviously pretty hard to change like a piece of silicon with a circuit on it. Okay, so I'll move this over here, and I will shift this table. All right, so take this, I'll move it over a little bit to give some room for the last column. There we go. And then finally, we'll have our S0 and R0. And we'll just quickly run through that. So if we're storing a 0, and at this point we're paying attention to that and to this here. So if we're holding a 0, want to hold a 1, that'll be 1, 0. If we're holding a 0, want to hold a 0, that'll be 0 star. If we're holding a 1, we want to hold a 0, that'll be 0, 1. If we're holding a 1, want to hold a 1, that'll be star 0. If we're holding a 0 and we want to hold a 1, that'll be 1, 0. Holding a 0, we want it to hold a 0, that's 0 star. Holding a 1, want to hold a 1, star 0, and then same situation. Holding a 1, want to hold a 1, star 0. And that's and this is like all of the possible different equations and truth tables all just put into one. Really, you would have one circuit here which doesn't use D1, D0, N0, N1, right? You only have Y1, Y0, X, Z, and then these. And then you have this one over here, which doesn't use any of the S and Rs or N1, N0, and just uses the rest. But we just sort of combined everything into one table because it's convenient for just filling things out and not having to write multiple tables. Okay, so now we can go ahead and start doing minimizations. I will go through some minimizations. There'll be some help there with just making sure you understand how to do K-maps. And yeah, also it'll help for covering how to do K-maps with Sr Latch, with don't cares, sorry, if you're not super comfortable with that. So let's see here. I guess I'll zoom out, make that table smaller. There we go. Okay, so what I'm going to do here is just draw out the K-map, and I'll reuse it for simplicity. So we have y1, y0 I'll have on top, and then I'll have my x on the side here. So then we can have 0, 0, 0, 1, 1, 1, 1, 0. Again, I'm going to repeat myself because definitely don't want you guys to make this mistake. Make sure you're numbering these things correctly, because otherwise that won't work. And like that with 0, 1. Okay. So now I should be able to draw and just erase that. Okay, perfect. Okay, so we'll just start off here with, let's say, Z. And actually, I will use a slightly different color here. So we have Z. Okay, so Z is here, is 1 here and here. So that's 1, 0, 1. So 1, 0, 1 and 1, 1, 0. Well, can't do anything there. So you just have to sort of come up with the terms individually. So we have that Z is equal to just both of the min terms. So we'll have y1, y0 not x, and or y1, y0 x naught. Which, if for those of you who have noticed this pattern before, this is actually the same thing as y1 and y0 x or x, but that's not really something that you need to worry about. And if you're doing a K-map, you don't need to worry about coming up with this. This is exactly the solution that you should get from a K-map, but this also happens to be equal here, right? This right here, this pattern right here, when it shows up, is XOR. Okay, so we'll go on to, let's say, D1. So for D1 here, we have ones all up here, quite a lot. I'll actually just write the zeros and then put the ones will be everywhere else. So the zeros are at 1, 1, 0, so 1, 1, 0, and 1, 1, 1, just right here. And it's 1 everywhere else. So 1, 1, 1, 1, 1, 1. Okay. So now we'll go ahead and start the circling. And I'm going to again run through my method of doing the K-maps that you should always be right. You should never be able to make a mistake. So we'll start off with 8. We can't do any circle of 8 because there's not 8 ones. Then we'll go down to 4 because again they have to be powers of 2 and they have to be rectangles. So here I can look at this one here. I can actually circle this one here in 2 different ways with 4. I can circle these 4 together, or I can sort of circle wrapping around these 4. Because of that, I'm going to wait to try to do any circle on this. And this is just to avoid giving any extra circles. But if I look at this one here, I can see that there's only one way to circle it in 4. It's this right here. So I know that that's correct, and I know that that's going to end up in my solution. So then I'll go over to these 2. I'll say, can I circle any of these in a circle of 4? The answer is yes. You can, again, do the wrapping. So it turns out that both of those were used. But the idea is if you have the option, you don't want to make that choice until you're absolutely certain that you want to include it in the final solution for your K-map. You only want to circle something if it's the only possible circle that one could be in, because obviously that's going to be good for your solution. And then you just focus on the uncircled ones from then on. So we end up with these two here. So our blue term here is going to be, so it's this column, and these two rows. So we see that y1 changes, so we won't include it. y0 is always 0, so we can include y0 not. And then x changes, so that'll just be that. And then we have our red box, which is going to be these two columns and these two rows, which means, so we can see here y1 is always 0, so this will be y1 not. Y0 changes and x changes, so that's our equation there. So then we can get, or those are our terms, and then we can just get the equation by, again, ORing everything together. So we have y0 not or y1 not. Next one. Let's see, let me go ahead and erase all of that. Oh. I'll go ahead and erase at least part of this here. Oh, sorry, that's not what I want to erase. I want to erase this. Okay, so then we'll go ahead and do D0. So that's 0, 0, 0. Or actually, I'll just go, I'll skip D0 for now, and I'll go on to, let's say, S0, because that one looks interesting. Just so we can take a look at the don't cares. You should be at least somewhat familiar with K-maps. So, yeah, let's see. So 0, 0, 0, that's the one there. 0, 1, 1 has a don't care. And we do want to put the don't cares. You don't necessarily need to put the zeros. The zeros do not matter in a K-map, but don't cares do matter because they could be a 1. And we'll make them a 1 if it's beneficial to make the equation more simplified. Yeah, well, so you have to give a value there. The don't care is going to be a 0 or a 1. There's no option. You can't say, oh, well, it's just, but what you're saying there when you're saying it's a don't care is it can be whatever it is. Like if it's a 0, that works. If it's a 1, that works. And we can use that fact to basically turn these don't cares into a 1 in the case that would make a bigger circle. Yeah, it's entirely a free card. Yeah, it's like just for example, if I have 3 1s here and I have a don't care here, well, I want to circle all these 4 together and just say, oh, well, I'm just going to make that don't care a 1 because that's way more minimized. Otherwise, you'd have to make these 2 circles here, and that's not as minimal. So, but we'll hopefully see that if this is a good example here. So 1 0 0, that has a 1 there, and then we have 1 1 0, which has a don't care, and we have to do 1 1 1, which has a don't care. All right, well, how do we do this? Well, we'll start off with a circle of 8. Can we make a circle of 8? The answer is no, because there's obviously not 8 1s. Can we make a circle of 4? We can't. Then we go down to 2. So with the don't cares, you sort of want to think of them as 1s when you're circling, but the difference between don't cares and 1s is that they don't have to be in a circle. So if you can avoid circling one, do so. The only time you should really be circling a don't care is if it helps to make a circle that contains a 1 bigger. So here, we'll just circle these 2 1s together and just leave the don't cares alone. I can't somehow make this circle bigger by including don't cares. So I'm just going to basically say, oh, well, actually, I'm just going to set all of these to 0. And that's actually way more minimized than if I were to do something else, right? Just because of the position of these don't cares, they're sort of bizarre. They're not going to be useful for this equation here. So we'll get that S0 is just the min term for this, which here we can see we have these 2 columns in this row. Y1 changes, Y0 is always 0, and X is always 0. So we'll have not X. So this will be Y0 not X not. Okay, and then we have, let's see. Oh. Sorry for that. And then we'll do R0. Okay, so we have 0, 0, 1 is a don't care. 0, 1, 0 is a 1. And then 1, 0, 1 is a don't care. That's pretty boring. Yeah, there's not really much we can do here. Right, this one is alone. It can't be circled with any of these don't cares. And so we're not going to just add extra ones in this, extra terms in this equation here for no reason. So we just end up with this here. We'll just end up with, yeah, I don't think any of these K-maps, looking at them, actually can use the don't cares in any meaningful way. Sort of interesting. Although, yeah, for every single one of these, I think we'll just end up setting the don't cares to 0 because that ends up being more minimized. Yeah, so this would just be the min term for that, which would be not y1, y0, x not, x not. And so we'll end up with r0 equals just, yeah, y1 not, y0, x not. And then you do that as well for the rest of them. So once you have those, right, you just implement this circuit. So you will basically just implement every single one of these, or for one of these two options, you would just implement them all in one of these boxes and then hook it up like this, and you're done. You have a functional FSM. There is some nuance in, there's actually some, it's actually kind of difficult to make sure that timings all work out, but we don't have to worry about that in this class. Like for the FSM lab, you just want to make sure you're following the directions carefully, because if you do something slightly different where the delays are too long or something like that, it can not work. So just make sure you're following the directions and doing as it says, just to make sure that once you're ultimately done and you run it, it'll actually work. It's not like that won't really matter for your grade, because I'm just going to look at the circuit itself. But if you want to actually see it work, you need to make sure you're following the directions so that everything works together. But yeah, so here I haven't, well, I guess I can't really quickly come up with equations for stuff, but well, let's say you come up with all the equations here, and then you'd sort of want to just look at, let's say we have our equation for D0. I'm just going to write something arbitrary, for example, here. These aren't the right equations, but let's say we have this. Actually, I can see not S1 is definitely going to simplify it to just not Y1. R0, or sorry, R1. R1 is just going to be Y1, Y0. And then D0, I don't know what it is. We'll just pretend that this is the equation for D0, but this is what you would get for S1 and R1. So then you would look at all of your equations here and you'd say, well, which would use less gates? Would it be cheaper to make this with the D latches or with the SR latches? You have to include Z regardless. That's going to have to be in your equation, in your circuit, because you need to compute the output regardless of whether you're using SR latches or D latches. However, you do want to take a look at, how complicated is my ultimate circuit if I make it with SR latches versus if I make it with D latches. For this class, when we say look at both of them and choose the more simplified one, we really mean like you choose the one that would use the least amount of gates. In reality, you would maybe look at the cost. Like you would go to your manufacturer and say, okay, well, how much would it cost to make this circuit versus how much would it cost to make this circuit? And you would literally just choose the cheaper one, because obviously they're going to both do the same thing. They're essentially going to be the same speed and do the same thing. So just choose the cheaper option. And once you have the actual equations, that allows you to actually figure out what those cheaper, what option would be cheaper. And in this case, I'm pretty sure the D latches end up being, well, with these equations, obviously the D latches are cheaper to make. Well, we have, actually I should probably work that out. So we have here a NOT gate, an OR gate, and a NOT gate. So this D1 uses 3 gates. Here we have a NOT gate, an AND gate, an OR gate. So that's 1, 2, 3. So in total, the D latches would use 6. Here we have not, and, which that's already 3. Here we have not, and, not, which you can sort of view as 3. You can also like have a 3 input AND gate, or sorry, you can view this as 4, as 2 different AND gates or something. This one is just a NOT gate, and this one is just an AND gate. And so here we end up with 9 total gates. So it would be cheaper to make the D latches. You can do that. It's not really a question that's too big of a deal. We don't really ask that too much. If we do, it'll usually be obvious. It might be like the D latches are super simplified, and the SR latches is really, really complicated or something. But yeah, it doesn't really. That's not really important. So, any questions on this? I know I've sort of gone on for a long time, but yeah, definitely go ahead and ask any questions, and I'll go back to whatever we need to. Well, you have the equation here, so you would just literally make this, right? So if I want to draw that out, I might draw, let's say, y1, y0, and x. So then we have our first term here, which I can draw in with an AND gate. That's a little bit small. I'll make it a little bit bigger. So we'll take y1, take y0, and invert it. Then we'll take x, so that's our first term. And then we have the second one, which is just going to be y1, y0, x, but then inverted, and then we'll just OR everything together. All right, so this here would be our z. And then like for the circuit itself, let's say we're using the SR latches, or let's say we're using the D latches. So D1 is this or this. So that we would just basically take in the same exact circuit. We would take y0, we would invert it, we would take y1, we would invert it, and then we would just OR those two together. And this would be our D1 output. And then you do the same thing for D2 in the case of D latches. Or if you had SR latches, you would replace these two with the equations for S1, R1, S0, and R0. Well, okay, let's see. Can I quickly go over how you went from truth table to finding the don't care zeros and ones? Yeah, I'll go over that. I'll quickly answer Justin's question. So the cost of the SR latch, it has to be all of these. If you're using SR latches, you have to implement every single one of these circuits, because you're going to have your, oh, that is not what I wanted. You're going to have your SR latches, and well, you have one for the Y0 state and one for the Y1 state. And you have to pass in both of these inputs into the one for the Y1 state, and you have to pass in both of these for the input of the Y2 state. And so, yeah, you're going to have, if you're using the SR latches, you're going to have to implement every single one of these if you're doing the SR latches. So you have to combine all their costs. And for the D latches, well, you're going to have to implement this circuit and this circuit. So that means you're going to combine their cost. And then you can just sort of ignore Z. Sometimes you can get it more minimized because you can maybe reuse something from Z inside of D1 or something. But I'll get to the SR latch stuff again. But okay, so does a D latch itself cost more than an SR latch? An SR latch is defined by a table. Anything which does what that table does is an SR latch. And anything which does the table for a D latch is a D latch. Logically, it sort of seems, and for the most part, logically, you have to use more components to make a D latch than an SR latch. But in reality, you can make D latches and SR latches non-logically. Most memory is made using something called DRAM, not SRAM. SRAM is what we talked about in class. It's where you use logic to actually make the components, and that's usually the fastest way to make memory. But DRAM uses a capacitor and a single transistor, which it's kind of hard to beat that's two components, and you can make essentially a D-latch out of that, or at least a cell for storing things. And so it's not entirely clear. It depends on how you're manufacturing the D-latches and SR latches. But yes, sometimes D-latch can cost more, sometimes it can cost less. It depends on what's made. And you may even want to use something like a JK flip-flop. I don't know. There's a whole bunch of different logical components. In theory, you would have to work out all of the different ones. And also, like, in reality, you're really going to be talking more about manufacturing cost. If there's a lot of manufacturers making just a lot of D-latches, but very few just making SR latches because they're not as useful, then it's possible that even if the D-latch is more expensive component-wise, it's cheaper to actually make, or something like that. So the cost is definitely a weird thing, and you can't really assume that the way that you would make a D-latch is the way that it would be made. It could be made in a bunch of different ways. Okay. So now for how you went from the SR truth table to finding the don't cares, zeros, and ones. So you were talking about that little lookup table for what if you have the current, next state, and then what S and R need to be for that. Okay. So again, this is not. I'm just clarifying this to make sure that no one thinks it is. This is not a truth table. This is just a lookup table for your convenience. Given the current state and the next state, what do S and R have to be? Okay, so let me move over here. So yes, I've been recording every single one of the reviews, and they're all posted on YouTube already. The link is on Canvas. Okay, so truth table for an SR latch. And really, we have a clocked SR latch, but we're just doing nothing when the clock is 0, and when the clock is 1, we're going to look at S and R and do something. So that we won't really worry about what the clock is. So we have 0, 0, 0, 1, and 1, 0, and I'm just going to leave 1, 1 out because it doesn't really matter. And when S and R are both 0, Q next is Q current. 0, 1, that'll be a 0, right? Because we're resetting to 0. And when S is 1 and R is 0, that'll be setting it to 1. Okay, so now we're trying to fill out this table. And essentially, well, actually, I can replace this here. So let's say you have an SR latch where Q current is this, and you want Q next to be this, right? This is essentially what we're asking here. So, well, we can literally just look up what happens in the SR latch, right? If we look just at this first row, we know Q current is 0. So I'll just go ahead and replace this. And we want Q next to be 1, to also be 0, sorry. So we want this to be 0. Well, obviously this row is wrong because the output's 1, right? That doesn't match what we want it to do. And so it ends up being that either of these two rows would work. Right, so I'm just going back up here. So again, either of these two rows will work. So S has to be 0, and we don't care what R is. The other way to think about this is if the SR latch is holding a 0 and you want it to hold a 0, you can either do nothing, because that would be right, or you could set it to a 0, which would also be right. Setting it to a 1 is obviously wrong because you want it to be a 0. Right, for the next one, we have 0, 1. So here it's currently holding a 0 and you want it to hold a 1. If we wanted to look at it, we know Q next is going to be 1, and we know Q current we want Q next to be 1, and we know Q current is 0. So, well, the only row that has Q next being 1 is this one. So S and R have to be this. Again, another way to look at it is, well, you have 3 options. You have maintain, which is this first one. You have set to 0, and you have set to 1. Okay, well, here, would maintaining the state work? Well, it's currently holding a 0, so if we maintain it as a 0, well, that wouldn't work, right? So we want it to be a 1. Okay, well, that maintain doesn't work. Set to 0, does that work? Well, if we set it to a 0, well, we want it to be a 1, so that's obviously not going to work. Or we can set it to a 1. Well, that would work here, right? So this row here is the only option that works. It's the only one that will actually produce the result that we want, and so it's the only valid input to the SR latches such that that state updates properly. for the next one, it's currently holding a 1, you want it to hold a 0. So maintaining doesn't work because they're different. Setting to 0, well, that does work. So this row does work because we want the result to be 0. Setting to 1 doesn't work because we want the result to be 0, not 1. So this is the only row that works. So it has to be this input. We have to input a 0, 1 into the SR latch so that it updates from the current state to the next state in this manner. Then we have the final one, 1, 1. So here now maintain does work, right? Because it's holding a 1. So if it stays a 1, that's fine. That works. Setting to 0 obviously doesn't work because we want it to hold a 1. And then setting it to 1, that also works because we want the output to 1. So if we just set it to a 1, that'll also work. So these two rows work, which means R has to be 0, right? Because in both of these rows, R is always 0. But S can be 0 or 1. Regardless of what it is, it'll work. So we can put a don't care there. Did that answer your question? Okay, perfect. Any other questions? And I do have everything as well, so I can go back to whatever we want. I'll ask one more time. Any other questions?